Hello and welcome to this video for Chemistry 20 in the Solutions unit. In this lesson, we're going to talk about dissolving and the process of dissolving and showing something called dissociation equations, which is showing what happens to a compound when it's put in water. So first of all, dissolving is not a chemical change. Dissolving is actually a physical change, which means it's easily reversible, okay? We're not changing our substances. We're not making new substances. All we're doing is breaking apart the bonds that either hold the ionic crystal lattice together or the intermolecular forces that hold a molecule together, okay? So this image here shows you sodium chloride. Sodium chloride being an ionic compound, and remember back to the bonding unit, ionic compounds, before you put them in water, are solid crystal lattice structures where you have positive and negative alternating ions. These molecules here are our water molecules, which are molecular. Okay? Now, in order for salt to dissolve in water, the water molecules have to spread apart from each other to make room for the new ions that are coming from the salt crystal. And the ionic bonds, again, of that crystal lattice have to break apart. So here we have a free sodium ion that's floating around in the water. And here is a free chloride ion that, I shouldn't say floating around, they're actually dissolved. So you can't really see them, but they are still there in the atomic structure floating around. Okay, now the water molecules also orient themselves. So water, remember, what this diagram is trying to show you for water is that you have a polar molecule because of the bent shape. So the oxygen end is slight negative, the hydrogen ends are slight positive. So the slight negative ends of the water molecules form a certain type of bond called an ion dipole bond that is forming between the negative end of the water molecule with a positive sodium ion, and here the positive hydrogen ions are aligning with the negative chloride ion. Okay, so the water molecules spread apart, the crystal lattice ionic compound breaks apart, and then you have new attractions forming between the ions and the water molecules. So the dissolving process involves these three stages. Number one, we have to break the bonds of the solute, whether it's ionic or molecular, depends on what bonds you're breaking, if they're a crystal lattice bond or if they're just intermolecular forces. But this step always requires energy. It's an endothermic process. We also have to break the molecules of the solvent, which again, if it's water, would be separating the London dispersion, dipole, and hydrogen bonds. Process is also requiring energy and endothermic. Now the third step is the new bonds being formed between the solute and solvent. That formation of bonds always releases energy and is exothermic. So whether or not the overall process requires or releases energy depends on the sum of the overall steps. If more energy is released when the new bonds are forming than is required to break apart the solute and solvent bonds, overall the dissolving process will be exothermic, and you will actually have heat being released during the process. So what that means is that, first of all, it'll happen without the addition of energy, so we can call that a spontaneous process where it'll happen without needing to add anything to make it happen, and in fact it's also going to also feel warm because it's exothermic. If, however, less energy is released than is required, then the overall process is going to be endothermic, and you're going to need to add energy or add heat to make the process happen because it won't happen on its own. Okay? This will also feel cool. When you make this process happen, it absorbs the energy from the surrounding environment, so it's going to feel cool during that process. Okay, so that's the steps of dissolving. Now let's talk about again how we show what happens to a compound when it's in water or it's in whatever solvent you're dissolving it in. Usually we deal with it in water. So first of all, we can classify or categorize our solutions into two categories. Either it is an electrolyte, which means it conducts electricity. Compounds that are electrolytes are, oh, there's some pretty effects here, all soluble ionic compounds, and very polar molecular compounds like acids and ammonia. Remember back in the Science 10 unit when we reviewed acids, we said that they were technically molecular because they share electrons, making a covalent bond. But when I put it in water, it actually ionizes. It breaks apart into ions, just like a soluble ionic compound would. And I'll show you what that process looks like in a minute. But if you have free ions floating around in solution, like we talked about actually in the bonding unit, when ions are able to move through a solution, a solvent of some sort, they will conduct electricity. Okay, and that's what an electrolyte means. It will conduct electricity. Your solution could also not conduct electricity, and those are called non-electrolytes. Okay, so electrolytes conduct electricity, non-electrolytes don't. And the reason non-electrolytes do not conduct electricity is because they do not form free ions. So in order to conduct electricity, you need free ions floating around in solution. That's like I showed in that first image of sodium chloride, where I had sodium ions and chloride ions. Right? That crystal lattice sodium chloride broke apart into those ions. So when we have these free ions, they conduct electrical currents. Molecular compounds do not form ions, so they do not conduct electricity. So we're going to look at showing this in a process called a dissociation equation. So a dissociation equation shows what's happening to what's happening to our solute when we place it in water. So you're going to start by showing the formula of the compound before it's in water, and then you're going to put an arrow and show what it looks like after it's in water. Okay? And there are 4 categories or 4 scenarios of what can happen to your compound when it's in water. Now, one thing I want to make a note of, your compound before it's in water is either going to be solid, liquid, or gas. It's never going to start aqueous because aqueous means it's in water. Okay, so you can never start with your compound as aqueous. It has to start as either solid, liquid, or gas. If it's ionic, remember all ionic compounds are solid before you put them in water. Molecular compounds can be solid, liquid, or gas. Okay, so let's look at our first of the 4 scenarios. Number 1, my compound, whether it's ionic or molecular, is insoluble. Okay, insoluble means it does not dissolve. For an ionic compound to determine if it's soluble or insoluble, we use the solubility chart. Okay? The solubility chart again was reviewed in Science 10, the Science 10 chemistry review, so you can go back to that video to watch if you need. The solubility chart again is for ionic compounds only. Molecular compounds that are insoluble are a lot of our hydrocarbons, a simple compound with C something, H something, okay? Unless it's a gas, because gases are very soluble based on the definition of solubility. But if I have this as a liquid or this type of compound as a solid, it is not going to be soluble, okay? So gasoline is C8H18 liquid, right? We know gasoline and water don't mix. Paraffin wax, C25H52. We know that when I take wax and put it on water, it doesn't dissolve, it just floats on top, right? So a lot of our simple hydrocarbons that are liquid or solid are insoluble. So how do we show a dissociation equation for an insoluble compound, whether it's ionic or molecular? It follows the same process. I write the formula of my compound again before it's in water. All ionic compounds start solid before they're in water. Then I put an arrow and I show that once it's in water, there is no change. Okay? The compound stays the exact same compound, it doesn't break apart, and the state stays the same. It starts as a solid, it ends as a solid. Okay? If it is insoluble, that is how you show a dissociation equation. This again was paraffin wax. C20, oh, when I wrote it up here, I wrote it wrong. C25H52. So when I have paraffin wax, before it's in water, it's a solid. Once I put it in water, it does not dissolve, it stays a solid. Okay, so your first of the 4 scenarios is that it is insoluble. When it's insoluble, what it looks like after it's in water is identical to what it looks like before it's in water. Okay, so that is the dissociation equation for an insoluble compound. Next, let's look at our second scenario of a soluble ionic compound. Okay, soluble ionic compound. Soluble ionic compounds, as I mentioned, form ions. They break apart into free ions in the solution. Okay, so the ionic bonds are broken. The solubility table again lets me know which type of ionic compounds are soluble, and this includes bases. Remember, bases turn litmus paper blue, and there's a lab that I do with my students where we identify solutions using conductivity. So a soluble ionic compound, because it's forming free ions, will be an electrolyte. So this compound will conduct electricity. Okay, it's basic if it contains the hydroxide ion. Okay, that's how you identify a base. And so remember, we can identify those in a lab scenario using litmus paper. Litmus paper again comes in 2 colors. It comes in red and blue. You dip them both in the solution. If both pieces of litmus paper are blue, then that means you have a base. That means you have an ionic compound that contains the hydroxide ions. Okay? Now, when you dissociate an ionic compound into its ions, you have to balance the number of ions, and I'll show you that in a second. But there's also a theory here that if your compound dissociates into multiple ions, and they're always going to dissociate into 2 ions, the cation and anion that make up the compound, but let's say I have a balancing coefficient of 2, in one reaction versus a balancing coefficient of 1. The more ions you have, the greater it's going to conduct electricity. Okay? That's actually a question for my students on their unit test. Now let's look at how we show the dissociation equation of a soluble ionic compound. So let's start with the most basic that we can have, sodium chloride. Now remember again, this is the compound before it's in water. Before ionic compounds are in water, they always start as solid. Now, when I put this compound in water, it will dissolve, it will turn aqueous, but not only will it turn aqueous, it also splits apart. So we always start with 1 mole of our compound, and it's going to break into 1 sodium ion. Again, because there's an invisible 1, right? We don't show those ones, but there's invisible 1 after the sodium and after the chloride. So I have a balancing coefficient of 1. Now to show sodium as an ion, I have to show its ion charge superscript. And again, its state is aqueous because it's dissolved in water. And then I put a plus, my second ion, which is the chloride ion. One of them, again, in this compound, and again, it is aqueous. Okay, now notice that this is not a decomposition chemical change where I'm forming the diatomic element chlorine gas. All right, this is not Cl2 gas that I'm forming. I am forming whatever ions are coming out of this compound, and any subscripts tell you how many of those ions there are. So the invisible ones there mean there's only 1 sodium and 1 chloride. Okay, you're never going to have Cl2. If you did have a compound, let's say you had 1 compound of, I want to make sure it's something that's soluble, so let me just grab the solubility chart here. Let's say I have calcium chloride. 1 calcium chloride molecule. Okay. Sorry, I shouldn't call that a molecule because it's an ionic compound. So it's an ionic compound, not a molecule. Molecular compounds are molecules. Anyway, I have my calcium chloride compound. That is soluble in water, and it will again dissociate into 1 calcium ion. My calcium ion has a 2+ charge, and now there's 2 chloride ions. I don't put a subscript, I put a balancing coefficient of 2. Okay, we never have subscripts with our simple ions. If they were a subscript in the compound, they become a balancing coefficient for our ion. Okay, that's very important. Now, if I had a compound like sodium phosphate, this would be like that. Again, my compounds are starting as solid because ionic compounds, before they're put in water, are always solid. Now, when I dissociate this, I have sodium ions and phosphate ions. Now, the phosphate polyatomic ion, that 4 is actually part of the ion. So that number does not become a coefficient. But for the sodium, this number does. I have 3 sodium ions and only 1 phosphate ion. That 4 is part of the phosphate ion, okay? It's almost like when you're writing the dissociation equation of a soluble ionic compound, it's like you're going backwards to writing the formula, right? Like if I told you, you have sodium phosphate, you would say, okay, I have sodium and I have phosphate. How do I make these charges balance? Well, I need 3 sodiums and 1 phosphate. Right? That's what we're doing. We're breaking it back apart into the 2 ions that make up that compound. It's always a cation, a positively charged ion, and an anion. Again, though, you can have multiples of each ions based on what was in the chemical formula. All right. Now, something like sodium phosphate would be more conductive than sodium chloride because sodium phosphate has 3 sodium ions, whereas sodium chloride has only 1. So the more ions that you have forming the balancing coefficient, in terms of balancing coefficients, you're going to have greater conductivity. Okay. Now, let's look at our next scenario, scenario 3. Where we have a soluble molecular compound, okay? My compound is soluble, but it's molecular. Molecular compounds are molecules, and they do not split into free ions. They stay a whole molecule, okay? They stay a whole molecule. So what this means is that they do not break into ions. They're not even made of ions in the first place, right? Because they're not ions in an ionic compound. And they are non-conductive. So they do not conduct electricity. They are non-electrolytes. So when I have a molecular compound, remember your common molecular compounds on the front of the periodic table. All of those common molecular compounds are soluble, right? There's no solubility chart for molecular compounds. So to determine solubility, if they're one of the common ones on the front of your periodic table, they will be soluble. And so again, we start with their state before they're in water. This is sucrose. It's a sugar, which is solid before it's in water, but it will dissolve. However, it does not split apart. The only thing that happens is it turns into aqueous. So it started as a solid and it becomes aqueous. Okay? We do not split it into ions. It is not formed of ions. Okay? So that is the first example. The next example we have, I'm just going to erase this because it's going to pop up here on my PowerPoint. Oh, that is the only example. Okay, well, let's make up another example. Let's say we have methane. Methane gas. Okay, all gases are soluble. Also, all gases are soluble. So here I have methane gas. When I put it in water, it will dissolve, but stay the whole methane molecule. Okay, so it does not dissociate. It will not conduct electricity, but it does dissolve. So it changes from a solid, liquid, or gas to aqueous. Aqueous meaning, again, it's dissolved in water. Okay, now let's look at our fourth and final scenario, acids. Now, acids make up their own category as I mentioned before, because they are technically molecular compounds. They share their electrons. However, they're a special category in that when I put them in water, they actually will form ions, even though they're molecular. Okay, they ionize. That's the word we use for them. For ionic compounds that split apart, we use the word dissociate. For acids, we use the word ionize because they're starting molecular and they're turning into ions. They're starting as atoms sharing electrons, turning into ions. Now, litmus paper, both pieces of litmus paper will turn red if you have an acid. And remember again, an acid is a hydrogen-containing compound. Now, we've always said acids are aqueous, right? They will be once they're in water, but most of the times they start as a gas or a liquid, okay? Or a solid. They could be either of those. So let's say we have H2SO4 gas, right? Before it's in water, it's not going to be aqueous yet. Now this, although it's molecular, is going to do what ionic compounds do. It's going to split into ions. It's going to split into 2 hydrogen ions because there was a subscript of 2, and there's only one sulfate, because if there was more than one sulfate, it would have had brackets around it with a number. Okay, so one of my H2SO4 gas compound is ionizing into 2 hydrogen ions and 1 sulfate ion. Okay, so acids, again, same idea, like you do with soluble ionic compounds, you split them into the 2 ions, the cation and anion that make them up. You don't split sulfate into the individual elements. Okay, you always have a cation and an anion, so 2 ions. There can be balancing coefficients in front of them, but there should only ever be 2 ions that you're dissociating your compound into. Okay? So that is the 4th scenario. Now let's look at some examples. So say you're asked to write the following dissociation equations, or you're asked to show what happens to each of the compounds when you put them in water. So when I'm doing this, I'm starting with identifying what type of compound I have. Potassium chloride is an ionic compound. Okay, so before it's in water, and again, when I'm writing an ionic compound, I have to balance ion charges. I have 1 potassium with 1 chloride. Before it's in water, all ionic compounds are solid. Okay? Now I have to check my solubility chart to see if it dissolves. A little hint here, if you ever have a group 1 ion, like potassium, sodium, lithium, hydrogen, they are all soluble. Okay, potassium is a group 1 ion, so it's soluble. So I have one of my compounds. It's going to split into 1 potassium ion, right, because that's all I needed to make that compound, and 1 chloride ion. So again, I'm showing them with their ion charges superscript. I'm showing their state as aqueous, and I'm using balancing coefficients to show how many of those ions were in the compound. So there was an invisible 1 for each of them. Next example, carbon dioxide. This is molecular. And carbon dioxide, you should be familiar with, is a gas. Now you can balance these two. I don't usually put balancing coefficients unless it's ionizing or dissociating, but you could say I have 1 carbon dioxide gas. It's forming 1 carbon dioxide aqueous. Okay, molecular compounds do not ionize, they do not break into ions, they just change their state from, in this case, gas to aqueous, because gases are soluble. Okay, next example, solid hydrogen nitrate. This is going to be an acid. Okay, because it starts with hydrogen, and it's letting us know the state of it because, again, this is molecular, so it could be solid, liquid, or gas. Hydrogen nitrate would be 1H with 1 NO3, and it's telling me that before it's in water, it's starting as solid. Now remember, acids will ionize, so it will break apart into one free hydrogen ion because there's one hydrogen ion in the compound, and one free nitrate ion because there's no brackets around the nitrate, which means there's only one nitrate ion in that compound. Okay, and again, your ions are always aqueous and they have an ion charge, a positive and negative ion charge. Next, we have aluminum sulfate. Aluminum has a charge of 3+ and sulfate has a charge of 2-. Okay, this is ionic because I have a metal with a nonmetal. And is it soluble? It is. When you check your solubility chart, it is soluble. Okay, so to start, I write the formula of this compound, balancing the ion charges. I have 2 aluminums and 3 sulfates to make them balance. So it's Al2SO4 in brackets 3. And again, this is before it's in water. It's starting as a solid ionic compound. All ionic compounds start solid. So when I dissociate this, because it is soluble, it'll dissociate, I'm splitting it apart into 2 free aluminum ions, because there was a 2 here, plus that came from how many of them I needed when I wrote the formula, right? That's what that 2 means. And then I also am breaking it apart into 3 sulfate ions. It took 3 of those ions to come together to balance with the 2 aluminums to make aluminum sulfate. So I have 2 Al3+ aqueous plus 3 SO4 2- aqueous. Okay. Next we have sodium phosphate decahydrate. This is a hydrated compound. What do we do with a hydrated compound? We haven't really looked at that yet. Okay. Hydrated compounds are also always ionic. I have sodium ions and phosphate ions making up this compound. And then I can kind of just ignore the hydrate to start in terms of determining the solubility. Sodium, again, a group 1 ion, so this will be soluble. So if I write the formula, I have 3 sodiums with my phosphate to make the ion charges balance. Then I put a dot, 10 for deca, hydrate means water. Okay, remember, hydrated compounds are still solid. Okay, this is water chemically bonded in the ionic crystal. It's still a solid compound. Now, when I dissociate it, I'm going to show again that it's splitting into 3 sodium 1+ aqueous ions and 1 phosphate ion. And I'm not even going to include water as a product because the aqueous means it's in water. So those 10 water molecules are just going to mix with the rest of the water. So on the product side for a hydrated compound, you just essentially ignore the hydrate. Okay? A couple more examples and then we are done. Gasoline. So gasoline, I would tell you what it is. It is C8H18. This is known as octane. It's a liquid. And this is a molecular compound. And remember I told you earlier that if it's a simple C something H something that's liquid or solid, it is going to be insoluble. Most of the time when we have molecular compounds given on a quiz, it'll tell you if it's soluble or insoluble since there's no solubility chart to check. So remember, if it's insoluble, what happens is nothing. Okay, it stays the exact same before and after it's in water. It's a whole compound and it's liquid. Barium sulfate is an ionic compound made of barium ions and sulfate ions. They actually balance with each other, so I need only 1 barium with 1 sulfate. And if I check my solubility chart, that is insoluble. So whether it's ionic or molecular, when it's insoluble, absolutely nothing changes from before it's in water to after it's in water. It stays a whole compound, it keeps its original state. Okay? Now, I think there's another slide just to explain again why it is that we are focusing on a solution or looking at a compound in water. And it's because chemical reactions, especially ions, if they're not free to move, the reaction will be very slow. So water acts as a solvent for those ions to separate, disperse, and collide, especially if they're ionic, so that the particle collisions can happen at a more quick rate, allowing the reaction to occur. Okay? And so that's it for this lesson. Thank you very much for watching.